In 1987, the physicist Lee Smolin was thinking about universes. Not just our universe, but all possible universes. He came up with an idea called cosmological natural selection. It was a bold theory. He suggested that whenever a massive star collapses into a black hole, a new universe is born on the other side of its singularity. This new baby universe inherits the physical laws of its parent, but with tiny, random changes. It's a cosmic version of biological evolution. Universes that have laws of physics good at making black holes will have more babies. Over countless eons, universes that are prolific black hole producers would come to dominate the multiverse. This idea forced physicists to think about the endpoints of stars. What happens when a star dies? The most massive ones create black holes, the theoretical parents of new universes in Smolin's theory. But what about the stars that are not quite massive enough? They don't just fade away. They collapse into something just as strange, something that teeters on the very edge of becoming a black hole. They become neutron stars. These objects are the leftovers of supernova explosion. They are cosmic relics, the densest objects in the universe that we can still directly observe. They are not black holes, but they are the next most extreme thing. And the laws of physics that govern them are so bizarre, they test the limits of our understanding. They are the perfect laboratories for a universe that might be fine-tuned to produce extreme objects. The properties of these stellar corpses sound like they were pulled from science fiction. But they are real. They are out there, scattered across our galaxy, spinning, pulsing, and challenging everything we thought we knew about matter. Number 17, they are the size of a city, but heavier than the sun. A neutron star is small. In cosmic terms, it's minuscule. The typical neutron star has a diameter of about 20 kilometers or 12 miles. You could drive across it in about 15 minutes if there were roads and you could somehow survive. This means an entire neutron star could fit comfortably inside the boundaries of a major city like London or New York. The Sun, by comparison, has a diameter of about 1.4 million kilometers. You could fit 70,000 neutron stars side by side across the face of the Sun. But that tiny size is deceptive. A neutron star contains an enormous amount of mass. The average neutron star has a mass about 1.4 times that of our Sun. Our Sun contains 99.8% of all the mass in our entire solar system. It is 333,000 times more massive than the Earth. A neutron star packs all of that and then some into a sphere no bigger than a city. This is the result of its formation. A neutron star is born from the collapse of a massive star, one that was originally between about 8 and 20 times the mass of our Sun. When this star runs out of fuel, its core implodes under its own gravity. The outer layers are blasted away in a supernova explosion, one of the most violent events in the universe. What's left behind is the collapsed core. Gravity has crushed the core so completely that the very structure of atoms is destroyed. In a normal atom, most of the volume is empty space. The nucleus is tiny and the electrons orbit far away. Under the immense pressure of a stellar collapse, the electrons are forced into the atomic nuclei. There, they combine with protons to form neutrons. The entire object becomes a tightly packed ball of neutrons, along with a smattering of other exotic particles. The only thing, stopping it from collapsing further into a black hole is, a quantum mechanical principle called neutron degeneracy pressure. This is a fundamental rule that says no two neutrons can occupy the same quantum state in the same place. It's an outward pushing force that, for a time, can hold gravity at bay. The result is an object with a density that is difficult to comprehend. The average density of a neutron star is around 10 raised to the power of 17 kilograms per cubic meter. For comparison, the density of water is 1,000 kilograms per cubic meter. The density at the center of the Sun is about 150,000 kilograms per cubic meter. A neutron star is 1 billion times denser than the center of the Sun. This combination of city-sized dimensions and superhuman mass is the foundation for all its other strange properties. It is the reason its gravity is so strong, its magnetic field so powerful, and its spin so fast. It all starts with putting more than a sun's worth of matter into a space smaller than a metropolitan area. The first neutron star to be identified with an optical counterpart was the one at the center of the Crab Nebula, a remnant of a supernova seen on Earth in the year 1054. For centuries, astronomers saw the beautiful nebula, but the tiny city-sized object powering it all remained hidden until technology caught up in the 1960s. Number 16, a teaspoon of one weighs more than Mount Everest. The density of a neutron star is its most famous and most mind-bending property. It is the result of cramming so much mass into such a small volume. The numbers are astronomical. Let's try to put it into perspective. A single cubic centimeter of neutron star material, a piece the size of a sugar cube, would have a mass of about 10 raised to the power of 14 grams. That is 100 trillion grams, or 100 billion kilograms. A standard sugar cube weighs about 4 grams. On Earth, we measure heavy things in tons. A car weighs a couple of tons. A blue whale can weigh up to 200 tons. A skyscraper like the Empire State Building weighs about 365,000 tons. A cubic centimeter of a neutron star weighs 100 million tons. If you could somehow bring a sugar cube-sized piece of a neutron star to Earth, it would instantly plummet through the ground. It would pass through the Earth's crust, mantle, and core as if they were empty space, pulled by gravity toward the center of the planet. It wouldn't stop until it reached the other side, and it would then oscillate back and forth through the Earth's core, eventually settling there. Another common analogy is a teaspoon. A teaspoon holds about 5 cubic centimeters of material. A teaspoon of neutron star matter would weigh around 500 million tons. Mount Everest, the tallest mountain on Earth, has an estimated mass of about 162 trillion kilograms, which is 162 billion tons. So a teaspoon of this stellar material would weigh about 5 billion tons. This is not quite the mass of Mount Everest, but it is in the same ballpark. It's the mass of about 900 Great Pyramids of Giza combined, all contained within the volume of a small spoon. This extreme density is not uniform throughout the star. A neutron star has layers, much like the Earth has a crust, mantle, and core. The outer crust is the least dense part, though by our standards it is still outrageously dense. Here you would find a lattice of heavy atomic nuclei like iron swimming in a sea of electrons. As you go deeper, the pressure increases. The nuclei get squeezed closer and closer together. They begin to deform and merge. This is where you find the bizarre phase of matter known as nuclear pasta. Deeper still, you reach the core, where the density can be several times higher than the average. Here, the matter is a soup of neutrons with some protons, electrons, and possibly more exotic particles like muons or even a quark-gluon plasma, the state of matter that existed just moments after the Big Bang. This density is the reason neutron stars are so stable, yet so close to collapse. The neutron degeneracy pressure that holds the star up is a direct consequence of this density. The neutrons are packed so tightly that their quantum nature prevents them from getting any closer. But there is a limit. If more mass is added to a neutron star, for example, by siphoning material from a companion star, it can exceed this limit. This is called the Tolman-Oppenheimer-Volkoff limit, and it is thought to be somewhere between 2 and 3 solar masses. If a neutron star's mass goes above this limit, neutron degeneracy pressure fails. Nothing can stop the final collapse, and the neutron star will become a black hole. Number 15, they spin faster than a kitchen blender. When a massive star collapses to form a neutron star, it conserves its angular momentum. This is the same principle a figure skater uses. When a skater is spinning with their arms outstretched, they spin slowly. When they pull their arms in, their rotational speed increases dramatically. The star is like the figure skater. It starts as a huge, slowly rotating object, perhaps rotating once every few weeks or months, when its core collapses from a sphere hundreds of thousands of kilometers across to one that is only 20 kilometers across. Its spin rate must increase to conserve that angular momentum. The increase is enormous. The result is that newborn neutron stars are spinning incredibly fast. A typical young neutron star might spin several times a second, but some spin much, much faster. These are known as millisecond pulsars. They are older neutron stars that have been spun up by accreting matter from a companion star in a binary system. As matter falls from the companion onto the neutron star, it transfers angular momentum, kicking the neutron star's spin up to incredible speeds. The fastest known spinning neutron star is called PSR J7482446 AD. It is located in the globular cluster Terzan 5, about 18,000 light-years from Earth. It was discovered in 2004. This pulsar rotates 716 times per second. That's 716 full rotations every single second. A typical kitchen blender blade spins at around 200 to 300 times per second on its highest setting. This neutron star spins more than twice as fast as that. Let's consider what that speed means for an object 20 kilometers in diameter. The circumference of such a star is about 63 kilometers. To complete a rotation 716 times a second, a point on its equator must be traveling at a fantastic speed. The calculation shows the equatorial speed is about 45,000 kilometers per second. This is roughly 15% the speed of light. The speed of light is the absolute cosmic speed limit. Anything with mass cannot reach it. The fact that this object can spin so fast without flying apart is a testament to its immense gravity. The gravitational force at the surface is so strong that it easily holds the star together, even at these rotational speeds. If it were to spin much faster, the centrifugal force at the equator would exceed the gravitational pull, and the star would begin to shed mass. This puts a theoretical upper limit on how fast a neutron star can spin, which scientists believe is somewhere around 1,000 to 1,500 rotations per second. We have not yet found one spinning that fast, but PSR J7482468 is already more than halfway there. Over time, neutron stars slow down. They emit beams of radiation from their magnetic poles. As these beams sweep through space, the neutron star loses rotational energy and its spin gradually decreases. This process is very slow, taking millions or billions of years. This is why the fastest pulsars are generally the older ones that have been recycled by a companion, while younger, isolated neutron stars spin fast, but not at millisecond speeds. The Crab pulsar, for example, is only about 970 years old and spins about 30 times per second. Number 14, their magnetic fields could wipe a credit card from the moon. The conservation of angular momentum that spins a neutron star up to incredible speeds also has a dramatic effect on its magnetic field. The original star had a magnetic field, just like our sun does. When the star's core collapses, the magnetic field lines get squeezed together and compressed into a much smaller volume. This process amplifies the magnetic field strength to astonishing levels. A typical refrigerator magnet has a magnetic field of about 50 Gauss. The Earth's magnetic field, which guides our compasses, is about 0.5 Gauss. The strongest magnetic fields created in a laboratory on Earth are on the order of a few million Gauss, but only for very brief moments. A typical neutron star has a magnetic field of around 1,010,000,000 raised to the power of 12 Gauss. This is 1,000,000,000 times stronger than the strongest magnet ever made by humans. A magnetic field this strong would have bizarre effects. If you were to get within about 1,000 kilometers of a typical neutron star, its magnetic field would distort the electron clouds of your atoms, effectively shredding your body at a molecular level. It is so strong that it can affect the vacuum of space itself. According to quantum electrodynamics, empty space is not truly empty. It is filled with a sea of virtual particles that pop in and out of existence. A powerful magnetic field can polarize this vacuum, a phenomenon known as vacuum birefringence. This means light passing through the magnetic field will be split into two polarized beams. This effect was predicted in the 1930s and was first observed in the light from a neutron star in 2016. But there is a class of neutron stars with even more powerful magnetic fields. These are called magnetars. Magnetars have magnetic fields that are up to 1,000 times stronger than a typical neutron star, reaching strengths of a quadrillion 10 raised to the power of 15 Gauss. A quadrillion is a 1 followed by 15 zeros. This is the strongest magnetic field known in the universe. The energy stored in a magnetar's magnetic field is greater than the energy it has in its rotation. A magnetar's magnetic field is so powerful it can have effects across vast interstellar distances. The analogy of wiping a credit card from the moon is an understatement. A magnetar could wipe every credit card on Earth from a distance halfway to the moon. In 2004, a magnetar named SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, erupted in a giant flare. This was caused by a starquake, a cracking of the magnetar's crust that rearranged its magnetic field. The burst of gamma rays and X-rays was so powerful that it traveled across the galaxy and hit the Earth's upper atmosphere. It partially ionized the ionosphere and was detected by numerous spacecraft. The event released more energy in 1/10 of a second than our sun has emitted in the last 100,000 years. If this magnetar had been within 10 light-years of Earth, the flare could have caused a mass extinction event. These objects are a reminder that the universe can produce forces far beyond our everyday experience. Number 13, the surface is hotter than the sun's core. A neutron star is born in the heart of a supernova. The collapse of the stellar core generates an incredible amount of heat. A newly formed neutron star can have a temperature of up to 1,010,000 raised to the power of 12 Kelvin. This is an almost unimaginable temperature. The core of our sun, by contrast, is a relatively cool 15 million Kelvin. However, this extreme heat does not last long. A newborn neutron star cools very rapidly through a process of neutrino emission. Neutrinos are tiny, almost massless particles that interact very weakly with other matter. They can escape from the dense core of the neutron star, carrying away a tremendous amount of energy. Within the first few minutes to a year, the temperature drops to around 1,000,000,000 Kelvin. Even after this initial rapid cooling, a neutron star remains incredibly hot. A young neutron star, one that is a few thousand years old, will have a surface temperature of around 1,000,000 Kelvin. This is still about 170 times hotter than the surface of our sun, which is about 5,800 Kelvin. Because they are so hot, neutron stars shine brightly in X-rays. This is one of the main ways astronomers detect them, especially those that are not pulsars or are too far away for their radio pulses to be detected. The telescopes, like the Chandra, the 10th Ray Observatory, are crucial for studying these objects. The interior of the neutron star is even hotter than its surface. There is a steep temperature gradient. While the surface might be 1,000,000 Kelvin, the core can remain at 100 million Kelvin for a very long time. The star's crust acts as an insulator, trapping the heat inside. The cooling process for an older neutron star is much slower. After the initial neutrino cooling phase, the star primarily cools by emitting photons light from its surface. This is a much less efficient process. It takes millions of years for a neutron star to cool down to a few 100,000 Kelvin. The study of neutron star cooling is a very active area of research. By measuring the surface temperature of neutron stars of different ages, scientists can learn about the properties of the matter in their cores. The cooling rate depends on the exact composition of the core. For example, if the core is a superfluid, it will cool differently than if it were a normal fluid. If there are exotic particles like pions or kaons present, they can open up new, more efficient neutrino emission channels, causing the star to cool faster. This is called the Urca process. By comparing observations with theoretical cooling models, physicists can place constraints on the equation of state of dense matter, one of the biggest unsolved problems in nuclear physics. Each temperature measurement of a neutron star is a piece of the puzzle, telling us something about the fundamental nature of matter under the most extreme conditions imaginable. Number 12. You would be crushed into a subatomic smear. The immense mass and tiny size of a neutron star combine to create a gravitational field of incredible strength. Gravity on the surface of a neutron star is about 200 billion times stronger than gravity on the surface of the Earth. A person who weighs 70 kilograms, about 154 pounds on Earth, would weigh 14 trillion kilograms on the surface of a neutron star. That's the mass of a small asteroid. Of course, you would never make it to the surface. The tidal forces alone would destroy you long before you got there. Tidal forces are caused by the difference in gravitational pull across an object. On Earth, the moon's tidal forces cause our ocean tides. The side of the Earth closer to the moon is pulled slightly harder than the side farther away. Near a neutron star, this difference is extreme. As you fell towards the star, the gravitational pull on your feet would be so much stronger than the pull on your head that you would be stretched apart. This process is known as spaghettification. You would be elongated into a thin stream of atoms. Let's assume you could somehow be placed on the surface without being spaghettified. The gravity is so strong that it would instantly flatten you. You wouldn't just be crushed into a pancake. The gravitational force would overcome the electrostatic forces that hold your atoms together. Your body would be compressed into a thin layer of degenerate matter smeared across the star's surface, just a few atoms thick. This intense gravity dictates the entire structure of the star. It is what makes the star a near-perfect sphere. Any mountains or other surface irregularities are flattened to an almost undetectable size. It is also what allows the star to spin so rapidly without flying apart. The escape velocity from the surface of a neutron star is enormous. On Earth, the escape velocity is about 11.2 kilometers per second. This is the speed a rocket needs to escape Earth's gravity. For a neutron star, the escape velocity is around 100,000 kilometers per second, which is about 1/3 the speed of light. Nothing, not even the fastest spinning piece of the star's equator, can escape its pull. The gravity of a neutron star also has profound effects on light. According to Einstein's theory of general relativity, gravity can bend the path of light. This is called gravitational lensing. The gravity of a neutron star is so strong that light rays from the far side of the star can be bent around it, allowing us to see parts of the back surface. If you were looking at a neutron star, you would be able to see more than 50% of its surface area at once. The light leaving the surface also has to climb out of a deep gravitational well. This causes it to lose energy, a phenomenon known as gravitational redshift. The light's wavelength is stretched, making it appear redder than it was when it was emitted. For a neutron star, this effect is significant and must be accounted for when analyzing its spectrum to determine its temperature or composition. Number 11. They have mountains millimeters high. Given the crushing gravity of a neutron star, you would expect its surface to be perfectly smooth. And it is, to an incredible degree. A neutron star is one of the smoothest objects in the universe, but it may not be absolutely perfect. It is possible for a neutron star to have mountains. However, these are not mountains in the terrestrial sense. A mountain on a neutron star would be a tiny bump on its incredibly rigid crust. The crust is thought to be a solid lattice of iron nuclei. This crust is extraordinarily strong, perhaps tens of billions of times more rigid than steel. This strength could support small deformations, but the star's gravity is always working to flatten everything out. The balance between the crust's strength and the immense gravity determines the maximum possible height of a mountain. Calculations suggest that the tallest mountain a neutron star could support would be only a few millimeters or at most a few centimeters high. A bump just 1 centimeter high on the surface of a neutron star would contain an enormous amount of mass and would exert a huge strain on the crust. Anything larger would cause the crust to crack and the mountain would collapse under its own weight. Why would a neutron star have these tiny mountains? They could be formed in a few ways. As a neutron star cools, its crust solidifies. This process might not be perfectly uniform, leading to bumps and irregularities. Another possibility is accretion. If the neutron star is in a binary system and is pulling matter from a companion star, this matter doesn't fall evenly onto the surface. It is funneled by the magnetic field onto the magnetic poles. This could lead to a buildup of material at the poles, creating a slight bulge, a mountain of accreted matter. Even a mountain that is only millimeters high can have significant consequences. If the mountain is not located on the star's rotational equator, it creates an asymmetry in the star's mass distributions. As the star spins rapidly, this tiny off-axis lump will generate ripples in the fabric of spacetime. These are called continuous gravitational waves. They are a different type of gravitational wave than the ones produced by the violent merger of two neutron stars or black holes. They are much weaker and have a constant frequency, like a steady hum, rather than a chirp. Detectors like LIGO and Virgo are constantly searching for these continuous gravitational waves. Finding them would be a major discovery. It would provide a new way to observe neutron stars, even those that are not pulsars. The signal from these waves could tell us about the star's spin rate, the size of its mountain, and the properties of its crust. So far, no definitive detection has been made, which suggests that mountains on neutron stars are either very small or very rare. But the search continues. These tiny millimeter high bumps on city-sized stars could open a new window into the universe. And number 10, the inside is made of nuclear pasta. Between the solid outer crust and the liquid core of a neutron star, there is a layer where matter is predicted to exist in some of the strangest forms imaginable. This is the realm of nuclear pasta. This phase of matter was first theorized in the 1980s by physicists studying the behavior of matter at extreme densities. As you descend through the crust of a neutron star, the pressure increases. The atomic nuclei, mostly iron in the outer layers, are squeezed closer and closer together. At a depth of a few hundred meters, the pressure becomes so great that the individual nuclei can no longer maintain their spherical shape. They begin to merge and deform. This is where the pasta phase begins. The name comes from the shapes the protons and neutrons are thought to form. There is a competition between two fundamental forces. The strong nuclear force tries to bind protons and neutrons together into clumps. At the same time, the electromagnetic force causes the positively charged protons to repel each other. In this dense environment, the most energy-efficient way for the particles to arrange themselves is to form complex geometric structures. At the top of the pasta layer, where the density is lower, the nuclei might form spherical clumps, surrounded by a sea of neutrons. Scientists call this the gnocchi phase. As the pressure increases, these clumps merge into long, cylindrical rods. This is the spaghetti phase. Deeper still, these rods can fuse together to form large, flat sheets like lasagna. This is the lasagna phase. After the lasagna phase, the roles of matter and empty space reverse. Instead of sheets of nuclear matter in a sea of neutrons, you get sheets of neutrons in a sea of nuclear matter. This is sometimes called anti-spaghetti or anti-gnocchi, where you have cylindrical or spherical voids in the dense nuclear matter. Finally, at the base of the crust, the matter dissolves into a uniform liquid of neutrons, protons, and electrons, which forms the outer core. This entire pasta layer is only a few hundred meters thick, but it could contain a significant fraction of the crust's mass. The properties of nuclear pasta are thought to be extraordinary. It may be the strongest material in the universe. Simulations suggest that it would be incredibly difficult to deform or break. Its unique structure would also affect how heat and particles move through the crust. For example, it could scatter neutrinos, affecting how the neutron star cools over time. It could also influence the electrical conductivity of the crust, which has implications for the evolution of the star's magnetic field. Because we cannot directly observe the inside of a neutron star, nuclear pasta remains a theoretical concept. However, evidence for its existence may be found in the behavior of neutron stars. The strength of the pasta layer could support the tiny mountains that generate continuous gravitational waves. It could also play a role in starquakes and the glitches observed in pulsar rotation rates. By studying these phenomena, scientists hope to find indirect evidence for these exotic, pasta-like structures deep inside a star. Number 9. They experience starquakes and glitches. Pulsars are some of the most precise timekeepers in the universe. The pulses of radiation they emit are, for the most part, incredibly regular. We can predict the arrival time of these pulses with astounding accuracy. However, sometimes this regularity is broken. A pulsar will suddenly, without warning, speed up its rotation by a tiny amount. This sudden change is called a glitch. Glitches are very small changes. The rotational frequency might increase by just 1 part in a million or even a billion. But because the timing of pulsars is so precise, these small jumps are easily detectable. After a glitch, the pulsar's spin rate will gradually relax back towards its previous rate of slowing down. Over 100 glitches have been observed in dozens of different pulsars since they were first discovered. The famous Vela pulsar glitches about once every 3 years. The exact cause of glitches is still an area of active research, but the leading theory involves the interaction between the neutron star's solid crust and its superfluid interior. The crust of the neutron star is rotating and is gradually slowing down due to the emission of radiation. The core of the neutron star, however, is thought to be a superfluid. A superfluid is a state of matter that has zero viscosity, meaning it can flow without any friction. Because the core is a superfluid, it is not rigidly coupled to the crust. The crust slows down, but the superfluid core continues to rotate at its faster speed, storing up a huge amount of angular momentum. The two components are only weakly linked. However, there is a limit to how much of a speed difference the system can tolerate. Eventually, some of the angular momentum from the rapidly spinning superfluid core is suddenly transferred to the slower spinning crust. This gives the crust a kick, causing its rotation to speed up in a glitch. The mechanism for this transfer is thought to involve vortices in the superfluid becoming pinned to the crystal lattice of the crust, and then suddenly unpinning like a spring, releasing its tension. Related to glitches are starquakes. These are seismic events on the neutron star, analogous to earthquakes on Earth. The crust of a neutron star is solid and rigid, but it is under immense stress from the star's intense gravity and powerful magnetic field. As the star spins down, its shape changes slightly. It becomes more spherical. This change can put a strain on the crust. The magnetic field can also shift and reconfigure, stressing the crust. Eventually, the stress can build up to the point where the crust cracks and rearranges itself. This is a starquake. A starquake can release a massive amount of energy. For a regular neutron star, a starquake could be the trigger for a glitch, as the cracking of the crust could allow the superfluid vortices to unpin and transfer their momentum. In magnetars, starquakes are thought to be the cause of the giant flares. The cracking of the crust allows the unstable magnetic field to reconfigure itself into a lower energy state, releasing a torrent of high-energy radiation in the process. The 2004 flare from SGR 1806 to 20 was likely caused by a major starquake that ripped through the magnetar's crust. Number 8. The core is a frictionless superfluid. Deep inside a neutron star, the conditions are so extreme that matter behaves in ways that are impossible to replicate on Earth. The core of a neutron star is a sea of densely packed neutrons. At the temperatures and pressures found there, these neutrons are expected to form a superfluid. A superfluid is a quantum mechanical state of matter. It is a fluid that flows with zero viscosity, meaning it has no internal friction. If you were to set a superfluid spinning in a container, it would continue to spin forever without slowing down. Superfluidity was first observed in liquid helium on Earth when it was cooled to just a few degrees above absolute zero. In a neutron star, the temperatures are hundreds of millions of degrees Kelvin. This sounds far too hot for superfluidity. However, the key factor is not just temperature, but the ratio of temperature to the particle's interaction energy. In the incredibly dense core of a neutron star, the neutrons are strongly interacting. This allows them to form Cooper pairs, similar to how electrons form Cooper pairs in a superconductor. These neutron pairs can then condense into a superfluid state, even at very high temperatures. The core of a neutron star is not just a superfluid of neutrons. It also contains a small fraction of protons and electrons. The protons are also expected to form Cooper pairs and condense into a superconductor. A superconductor is a material that can conduct electricity with zero resistance. So the core of a neutron star is thought to be a unique mixture of a neutron superfluid and a proton superconductor, all intermingled. This has profound consequences for the star's properties. The fact that the core is a superfluid is central to the leading theory of pulsar glitches. The frictionless nature of the core allows it to rotate independently of the crust, storing angular momentum that can be suddenly released. The superconductivity of the protons plays a crucial role in the star's magnetic field. In a normal conductor, a magnetic field would decay over time due to electrical resistance. In a superconductor, magnetic fields can persist for extremely long periods. The proton superconductor in the core is thought to be responsible for locking in the neutron star's powerful magnetic field, allowing it to survive for millions or even billions of years. The properties of the superfluid and superconducting core also affect how the neutron star cools. The formation of Cooper pairs opens up new channels for neutrino emission, which can accelerate the cooling of the star in its early life. By observing the temperatures of neutron stars of different ages, astronomers can test these theories of superfluidity and superconductivity in dense matter. The neutron star is a cosmic laboratory where we can study these exotic quantum states on a stellar scale. Number 7, they bend time and space around them. Albert Einstein's theory of general relativity, published in 1915, describes gravity not as a force, but as a curvature of space-time caused by mass and energy. The more massive and dense an object is, the more it curves the space-time around it. A neutron star with the mass of a sun packed into the volume of a city creates a very steep curve in space-time. This curvature has several observable effects. One is gravitational lensing, where the path of light is bent as it passes by the star. As mentioned earlier, this allows us to see parts of the back of the star, but the curvature of space-time also affects the flow of time itself. This is called gravitational time dilation. Time runs slower in a stronger gravitational field. This is a real measurable effect. The clocks on GPS satellites, which are in a weaker gravitational field than we are on the surface of the Earth, actually run slightly faster than clocks on the ground. The difference is small, only about 38 microseconds per day, but it is enough that it must be corrected for if the GPS system is to work accurately. Near a neutron star, this effect is much more extreme. Time on the surface of a neutron star runs significantly slower than time far away from it. A clock on the surface of a typical neutron star would tick about 20% to 30% slower than a clock in deep space. This means that if you could watch a clock on a neutron star's surface from a safe distance, you would see it secondhand take about 1.2 or 1.3 seconds to complete each tick, compared to your own clock. If you were to spend a year on the surface of a neutron star, assuming you could survive, more than a year would have passed for everyone else in the universe. Another consequence of this strong space-time curvature is the precession of orbits. In Newtonian physics, a planet in orbit around a star follows a perfect ellipse that never changes. In general relativity, the orbit is not a closed ellipse. It is a rosette pattern that slowly precesses, or rotates, over time. This effect was first observed in the orbit of Mercury around our Sun. The precession is very small, only 43 arcseconds per century, but it was a major confirmation of Einstein's theory. For a system with a neutron star, the precession is much more dramatic. The best examples are binary pulsar systems, where two neutron stars, or a neutron star and another star, orbit each other. The Hulse-Taylor binary pulsar, discovered in 1974, was the first such system where these relativistic effects were measured with high precision. The orbit of this system precesses by a whopping 4.2 degrees per year. This is tens of thousands of times larger than the precession of Mercury's orbit. The precise measurement of this and other relativistic effects in the Hulse-Taylor system provided the first indirect evidence for the existence of gravitational waves, and earned its discoverers the Nobel Prize in Physics in 1993. Number 6. They are the universe's gold factories. For a long time, the origin of the heaviest elements in the universe, like gold, platinum, and uranium, was a mystery. We knew that lighter elements up to iron are forged in the cores of stars through nuclear fusion. We also knew that the supernova explosions of massive stars could create some elements heavier than iron. However, detailed models of supernovae showed that they could not produce enough of the heaviest elements to account for the amounts we see in the universe today. The creation of these heavy elements requires a process called the rapid neutron capture process, or R process. This process requires an environment with an extremely high density of free neutrons. In such an environment, an atomic nucleus can rapidly capture many neutrons before it has a chance to radioactively decay. After the neutron capture phase is over, these neutron-rich nuclei undergo a series of beta decays, where neutrons turn into protons to become stable, heavy elements like gold and platinum. Supernovae are rich in neutrons, but for a long time it seemed they were not quite rich enough. A new candidate for the site of the R process emerged: the merger of two neutron stars. When two neutron stars in a binary system orbit each other, they radiate gravitational waves. This causes them to lose orbital energy and spiral closer together. Eventually, they will collide and merge in a violent event known as a kilonova. This merger is one of the most cataclysmic events in the universe. In the final moments of the merger, huge amounts of neutron-rich material are ejected into space at high speeds. This ejected material is the perfect environment for the R process to occur. The density of neutrons is incredibly high, far higher than in a typical supernova. Models predicted that a single neutron star merger could produce a large amount of heavy elements, enough to potentially solve the mystery of their origin. This theory remained a prediction for decades. Then, on August 17, 2017, it was confirmed. The LIGO and Virgo gravitational wave detectors registered a signal, GW17181817, from the inspiral and merger of two neutron stars. Just 1.7 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of the sky. Telescopes all over the world were pointed to the location. They saw a new point of light, a kilonova in the galaxy NGC 4993, about 130 million light-years away. For the next few days and weeks, astronomers watched as the light from this kilonova evolved. Its spectrum changed over time. The light initially was blue, but it quickly reddened. This color change was the smoking gun. It was the signature of heavy R process elements being created in the ejecta. These newly synthesized elements are opaque to blue light, so as they formed, they blocked the blue light and made the kilonova appear red. Spectroscopic analysis later identified the signature of specific heavy elements, such as strontium. While gold itself was not directly detected, the conditions were certainly right for its creation. It is estimated that this single merger event may have produced up to 10 Earth masses of gold and platinum. Most of the gold in your jewelry, the platinum in a catalytic converter, and the uranium in a power plant was likely forged billions of years ago in the cataclysmic collision of two dead stars. Number 5, their collisions create gravitational waves we can detect. Gravitational waves are ripples in the fabric of space-time predicted by Albert Einstein in 1916. They are created by the acceleration of massive objects. For most of the 20th century, these waves were purely theoretical. They are incredibly weak and difficult to detect. The challenge is that as a gravitational wave passes, it stretches and squeezes space-time itself. The effect is minuscule. A strong gravitational wave passing through the Earth might stretch our planet by less than the width of an atomic nucleus. Detecting such a tiny change required incredible technology. This came in the form of the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two identical detectors, one in Louisiana and one in Washington state. Each detector is an L-shaped instrument with two 4-kilometer-long arms. A laser beam is split and sent down each arm. The beams reflect off mirrors at the ends and return to the corner where they are recombined. If the lengths of the two arms are identical, the light waves should cancel each other out. But if a gravitational wave passes through, it will slightly stretch one arm and squeeze the other, changing their lengths. This causes the light waves to no longer cancel out perfectly, creating a signal. On September 14, 2015, LIGO made the first ever direct detection of a gravitational wave. The signal, GW1391, came from the merger of two black holes. This was a monumental achievement that opened a new era of astronomy. Since then, LIGO and its European counterpart, Virgo, have detected dozens of signals from black hole mergers. But on August 17, 2017, they detected something different. The signal, GW17817, was much longer than the ones from black hole mergers. It lasted for about 100 seconds. The analysis showed that it was produced by two neutron stars spiraling into each other. Black hole mergers are invisible. They produce no light. But the merger of two neutron stars was predicted to create a spectacular fireworks display across the electromagnetic spectrum, a kilonova. The detection of GW17817 triggered a global astronomical campaign. The ability to observe the same event in both gravitational waves and light, known as multi-messenger astronomy, provided a wealth of information. The gravitational wave signal told us the masses of the two neutron stars, their distance from us, and the dynamics of their merger. The electromagnetic observations, from gamma rays to radio waves, told us about the kilonova explosion, the creation of heavy elements, and the nature of the object that was left behind after the merger. This single event provided a treasure trove of scientific results. It confirmed that neutron star mergers are a source of short gamma ray bursts. It confirmed that they are a major site of our process, nucleosynthesis. It allowed for a new, independent measurement of the expansion rate of the universe. It also placed tight constraints on the equation of state of neutron star matter. By analyzing how the neutron stars deformed due to tidal forces just before they merged, physicists could rule out some models of what the inside of a neutron star is like. The study of gravitational waves from neutron star mergers is a powerful new tool to probe the most extreme matter in the universe. Number 4, they are not actually made of neutrons. The name neutron star is a bit of a misnomer. While neutrons are by far the most abundant particle, a neutron star is a much more complex object. It contains a diverse soup of particles, and its exact composition is one of the biggest mysteries in modern astrophysics. Well, let's break it down by layer. The very outermost layer, the atmosphere, is only a few centimeters thick. It is made of hydrogen, helium, or carbon, depending on the star's history. Below this is the outer crust, which is a few hundred meters thick. This is a solid lattice of atomic nuclei, mostly iron, similar to the structure of a metal on Earth. These nuclei are surrounded by a sea of free-flowing electrons. Deeper down is the inner crust. Here, the pressure is so high that the nuclei are neutron-rich. They have absorbed so many neutrons that they are far beyond the stability seen in terrestrial elements. This is also where the nuclear pasta phase is thought to exist, with nuclei deforming into spaghetti, lasagna, and other shapes. Below the crust is the core, which makes up the bulk of the star's mass and volume. The outer core is thought to be a uniform liquid composed primarily of neutrons, but with a small percentage, around 5 to 10% of protons, and an equal number of electrons to maintain charge neutrality. This mixture of particles is what is believed to form the neutron superfluid and proton superconductor. The composition of the inner core is the biggest unknown. The densities here are several times that of a normal atomic nucleus. At these densities, our current understanding of nuclear physics breaks down. We simply do not have the experimental data or the theoretical tools to say for sure what matter is like under these conditions. There are several competing theories. One possibility is that the inner core is still made of neutrons, protons, and electrons, just at a higher density. Another possibility is that new exotic particles begin to appear. The immense pressure might be enough to create hyperons, which are particles that contain strange quarks, in addition to the up and down quarks that make up protons and neutrons. Or the pressure could create a Bose-Einstein condensate of other exotic particles like pions or kaons. The most extreme possibility is that the pressure in the inner core is so great that the neutrons and protons themselves are crushed. The quarks that make up the neutrons and protons would be liberated, forming a new state of matter called a quark-gluon plasma. This is the same state of matter that is believed to have existed for the first few microseconds after the Big Bang. If this is the case, the object would be a quark star or a hybrid star with a core of quark matter surrounded by a mantle of neutron matter. Determining the true composition of a neutron star's core is a major goal of physics. Scientists are trying to tackle this problem by studying gravitational waves from mergers, by precisely measuring the masses and radii of neutron stars, and by observing how they cool. Each piece of data helps to constrain the equation of state, the relationship between pressure and density, which in turn tells us what the star is made of. Number 3, they can come back from the dead. An isolated neutron star is, for all intents and purposes, a dead star. It is the remnant of a star that has exhausted its fuel and exploded. It no longer generates energy through nuclear fusion. It is simply a hot, dense cinder that is slowly cooling and spinning down over billions of years. However, if a neutron star is in a binary system with another star, its life can be very different. It can experience a form of rejuvenation, coming back from the dead. If the companion star is close enough, the neutron star's powerful gravity can pull material from its outer layers. This material, mostly hydrogen and helium, does not fall directly onto the neutron star. Instead, it forms a swirling hot disk of gas around it, called an accretion disk. As the gas in the accretion disk spirals inward, it gets incredibly hot due to friction, reaching temperatures of millions of degrees. This causes it to emit intense X-rays. These systems are known as X-ray binaries, and they are some of the brightest X-ray sources in the sky. The neutron star itself is not producing this light, but its gravity is the engine that powers it. The material from the accretion disk eventually falls onto the surface of the neutron star. This process of accretion has two major effects. First, it transfers angular momentum to the neutron star, spinning it up. This is the process that creates the ultra-fast millisecond pulsars. An old, slow-spinning neutron star can be recycled or spun up by accretion, becoming one of the fastest rotating objects in the universe. Second, the accreted material piles up on the neutron star's surface. This layer of fresh hydrogen and helium gets compressed and heated by the star's gravity. When enough material has accumulated, the pressure and temperature at the bottom of the layer can become high enough to trigger runaway thermonuclear fusion. This is essentially a giant hydrogen bomb going off on the surface of the star. This sudden burst of fusion releases a tremendous amount of energy in a very short time, producing a flash of X-rays that can be observed from Earth. These events are called type I X-ray bursts. They can cause the X-ray brightness of the system to increase by a factor of 100 in just a few seconds. After the burst, the system returns to its normal brightness and the process of accretion begins again. These bursts can recur on timescales of hours to days, depending on the rate of accretion. So, a neutron star in a binary system is far from dead. It is an active, dynamic object powering bright X-ray emissions, spinning up to incredible speeds, and periodically erupting in thermonuclear explosions. It is a cosmic vampire, feeding off its companion to reignite its fire. Number 2, some are completely silent. When most people think of a neutron star, they think of a pulsar. A pulsar is a neutron star that emits beams of radiation from its magnetic poles. As the star rotates, these beams sweep across space like a lighthouse beam. If one of these beams happens to sweep across the Earth, we detect a regular pulse of radio waves. This is how Jocelyn Bell Burnell first discovered them in 1967. For a long time, it was thought that all neutron stars were pulsars. But we now know that this is not the case. A neutron star only acts as a pulsar under certain conditions. First, it needs to have a strong magnetic field and be rotating fast enough to generate the radiation. Over time, a neutron star's rotation slows down, and its magnetic field may decay. Eventually, it will slow down so much that it can no longer produce the radio emission. It crosses a death line in the pulsar diagram and becomes a silent, radio-quiet neutron star. Our galaxy is likely filled with billions of these dead pulsars, old relics that are now invisible to our radio telescopes. Second, the lighthouse beam must be pointed at us. A neutron star's rotational axis, the axis it spins around, is generally not aligned with its magnetic axis, the axis connecting its magnetic poles. The beams of radiation come from the magnetic poles. If the geometry is such that the beams never sweep across the Earth as the star rotates, we will never see it as a pulsar, no matter how fast it is spinning or how strong its magnetic field is. It is estimated that we only see a fraction, perhaps 10 to 20%, of the active pulsar population due to this geometric effect. So, how do we find these silent neutron stars? We have to look for other signatures. One way is to look for them in X-rays. Young, hot neutron stars will glow in X-rays due to their residual heat from the supernova explosion. By searching supernova remnants for faint, point-like X-ray sources, astronomers have been able to find several neutron stars that are not visible as radio pulsars. A group of these objects is known as the Magnificent Seven. These are 7 nearby, middle-aged, isolated neutron stars that are radio quiet but shine brightly in X-rays. They are a valuable laboratory for studying the cooling of neutron stars. Another way to find them is through their gravitational influence. If a silent neutron star is in a binary system, we can sometimes infer its presence by observing the motion of its companion star. And, of course, with the advent of gravitational wave astronomy, we can now hear the collisions of silent neutron stars from across the universe. EW-781 was a merger of 2 neutron stars, and it is likely that at least one of them was not a pulsar we could have detected with radio telescopes. The universe is full of neutron stars that are not flashing lighthouses. They are dark, silent objects waiting to be discovered by other means. Number 1, they live on the edge of becoming a black hole. A neutron star exists in a delicate balance. Its immense gravity is trying to crush it into a singularity. The only thing holding it up is neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed into the same space. But there is a limit to how much mass this pressure can support. This limit is known as the Tolman-Oppenheimer-Volkoff TOV limit. It is the maximum possible mass for a non-rotating neutron star. If a neutron star exceeds this mass, degeneracy pressure will fail and nothing can stop the relentless pull of gravity. The star will collapse in on itself, forming a black hole. The exact value of the TOV limit is not known precisely. This is because it depends on the equation of state of the matter inside the neutron star, which is still uncertain. Different models of the core's composition predict different values for the maximum mass. Most current estimates place the TOV limit somewhere between 2.0 and 2.5 solar masses. This creates a mass gap in the population of compact objects We have observed many neutron stars with masses up to about 2.0 solar masses. The most massive, well-measured neutron star is PSR J0740 plus 6,620 with a mass of about 2.14 solar masses. We have also observed many stellar mass black holes, with the lightest ones starting around 5 solar masses. The region between about 2.2 and 5 solar masses seems to be empty. We haven't found any neutron stars or black holes with masses in this range. The existence of this gap suggests that the TOV limit is likely around 2.2 solar masses. Any object more massive than that, born from a stellar collapse, becomes a black hole. This means that all neutron stars live their lives on the precipice of oblivion. A neutron star with a mass of 1.4 solar masses is stable, but if it is in a binary system, it can accrete mass from its companion. As it gains mass, it gets smaller and denser. Its gravity gets stronger, it creeps closer and closer to the TOV limit. If it accretes enough mass to cross that threshold, it will undergo a final, catastrophic collapse. This process is called accretion-induced collapse. It is thought to be one way to form stellar mass black holes. The collapse itself would be an incredibly violent event. It would likely produce a powerful burst of neutrinos and gravitational waves. It might also produce a short gamma ray burst, though this is less certain. The 2017 neutron star merger GW17817 provided a fascinating glimpse into this process. The two merging neutron stars had a combined mass of about 2.7 solar masses. This is above the TOV limit. So the object that formed after the merger must have eventually collapsed into a black hole. However, it may not have collapsed immediately. The remnant could have been temporarily supported against collapse by its rapid rotation, forming a short-lived hypermassive or supermassive neutron star. This object would have survived for a fraction of a second to perhaps a few hours before shedding its excess angular momentum and succumbing to gravity. Every neutron star is a monument to a battle between gravity and quantum mechanics. It is a testament to matter pushed to its absolute limit, but that limit is a hard one. A single extra particle of mass at the right moment can be the difference between a stable star and an eternal black hole.